which is the introduction to group theory. Now, we don't want to introduce group theory just to make it complicated. In fact, there's really a couple reasons. One is to connect back to the fact that even though we're doing a lot of geometric things here, it's actually connected mathematically back to group theory. That is that the rules in which we are operating, as you'll see, are connected to the definition of a group. And we kept on saying, for example, when we try to do fivefold and we combine it with translation vector and it doesn't fill space, another way of saying that is that they really can't be a member of the same group. Okay, and so there's value in both connecting to a field of mathematics, but it's also valuable to us in terms of thinking later about how in a group, once you start thinking that way, the combination of two elements in a group can lead to another member of the group. So if there's, for example, one of the combination theorems which you introduced earlier, we haven't gone into that, and we'll get into that after this lecture, but these combination theorems where, like, if I have two mirror planes, it automatically means something and induces another thing, like a rotation, for example, then it tells you that that rotation is a member of the group, which means it's in that pattern somewhere, right? And that's where the combination theorem comes from, because the combination theorem tells you where to find it, okay? So all these things are connected, right? So we just want to do a little intro to make sure you can see that connection. And of course, in some future data, if you wanted to get into more of the mathematical basis for the grouping of these patterns and things like that, then obviously group theory would be where you go. So a group is a set of elements. I was just kind of implying that with my introduction. And really, this may seem a bit circular, but it's not, because, well, what's an element? An element is a thing in which there are laws describing how the elements are combined. So there are rules, and these rules determine, what the elements are and can exist in a group. So let's talk about that a little bit. So these elements will satisfy group postulates. These are the laws, right? And a combination of two elements is also a member of a group. This is what I was just talking about. So if you have a full group and it's not a subgroup, then what it means is that if you have operators in that group, if I'm choosing to, because group theory is general, you could have numbers in there, you can have operators in there, you can have whatever. So if I have two operators, and that's what we're gonna have, because remember, these mirror plane, the rotations, they're all operators, right? So a combination of any of those two, if they result in a new operation, like we've talked about, then that operation is also an element of the group, and that crystal group, we're going to be talking about crystals because we're going to eventually put atoms in here. But remember how we're deriving this all just from pure geometry, right? So here we have, well, these geometries, the way it works out is, the elements in them are part of a group, and we might not be able to see initially, for example, some sort of symmetry in our geometry, but then we look at some of these combination theorems and say, well, hey, if I have two mirror planes like that, it automatically means I have a rotation over here, and that'll show us that there's a rotation there, and we might not have seen it by observation. Right now, again, we're kind of started with observation because it's very didactic and people, can grow into understanding what's going on. But when things get more complicated, we have to move away from just simple observation and go to postulates, which help us determine everything. And you probably remember that from geometry, where there's certain obvious things you can see just by looking at the picture. But then we had to create theorems, right, which cover more complicated situations where I might not be able to see everything just by observation. So it's the same thing here. So one of the rules is that, two elements, a combination of two elements in a group create another member of the group if such a combination produces something. The identity operation as part of the group, this won't be as initially as important it seems, but all it's saying is that if I, and this is an I for identity element, and an identity element has these properties where if I operate on it, I actually have the same thing as if I operated the identity operator on another element, and all those things are just equal to the element itself. It doesn't actually transform it into anything, right? So you have to have an identity operation, and then also for every element there's an inverse, which means that if I have element A, there exists some inverse that when I operate with the inverse on A, I get the identity element, and of course the opposite. If I have A, if A operates on its inverse, it gives you the identity element. So very mathematical, probably initially not going to be very important to us, but we're gonna show you how to do this and identify the group, and that's why you'll notice that for our operations, 1 is an identity element and it'll appear everywhere. Mathematically, this is not our operations. We're going to use numbers now, but we just want to get used to some concepts. So for example, a very simple example, a set, right, a group could be these two numbers, 1 and minus 1. So let's see if that's the case, right? So remember everything I was just showing you, these kind of, remember the identity, the inverse, and the elements, two elements combining to produce another element. These are all operating between the elements. Remember when I was showing you identity, it was this on that, this on that. So the way that you can save yourself some time, since we're just doing all the combinations of these guys operating on each other to test all these things, you can make a group multiplication table or identity matrix, whichever you want to call it, and you can put the elements of this set along 1, and then we put the set along the other, and of course all you're going to do is let one operate on the other, right? So for example, oops, I should put this. So the way this works is that we'll have this one, right, and then we'll operate on by this one. So this operated on that gives us a 1. This operated on that gives us a minus 1. This operating on this gives a minus 1, and this operating on that gives a 1, right? And so if you notice, an identity element is 1 along the diagonal typically, because when you do itself, you should get identity element. So when you have something operating on itself, remember you should get identity element. So we have that, so that's checked. The inverse exists, and clearly when we combine, we always get the other element, right? So that's a very simple example of satisfying these 3 criteria. Another example, which we'll leave for you to prove to yourself. Sorry, it's a 1. So you can do this one out if you want. Where I is the square root, it's an imaginary number. And so that would be a group as well because it satisfies all these things. So there's a little deviation of math for you. And I think that that's all we need to do there to show you how we can use this matrix to help identify the three conditions for a group. Now, we haven't created groups with many things in it, right? So all the groups have right now just an identity element in itself, right? So the only point groups, and now here's some terminology. So I put this term point. And what I mean is that if you look at these 6 operations, they operate on a point, right? Obviously, rotations operate on a point, right? Because you're rotating about there. We talked about a alpha. M operates on a set of points, but about somewhere. So, for example, if I put M here, and I have something here, it gets reflected over here. So there's a line of points on which it operates, and so these are pretty simple because there's nothing else in the element, just that one thing, and that's why we haven't done anything. But what we haven't done is look at, well, what happens if I combine these elements? Because remember, this could be a subgroup, right? If I have just a simple twofold axis, this could be the only thing, right? We showed that in the oblique lattice, it's there, right? On the other hand, there might be other, when this interacts with other things in here, like a mirror plane, whatever, this could actually be a subgroup of a larger group, and we just haven't seen that more complex crystal structure yet. So we want to get into that, and the way we're going to get to is exactly what I said, which is we've generated these lattices by letting these things operate on a translation vector. What we haven't done is let the mirror planes interact with these elements, producing possibly new elements in a different kind of point group. And again, these are all point groups because there's no translation vector, right? Or operator, I should say. So, we're not moving this. So even if I do the mirror plane or I do the rotation, we're not doing this over and over again and making sure it's compatible or anything like that, right? So that's why they're called point groups. Now, after we develop the point groups, we're going to want to, come back and actually do something by creating more complex crystal structures by then putting these point groups in lattice points, okay, and then seeing, what that generates. So looking forward then, these point groups that we have already developed, we're going to develop some new ones, and you can see what the new ones on the chart are going to be here. But so we have our lattices. Remember, we had our oblique lattice. We have a primitive rectangular, a center rectangular, a square, and a hexagonal. Now remember what we did here. These essentially have the translational acceptance, right? They had the infinite number of elements in their group, if you will, because they repeat forever, right? The point groups we've been talking about, for example, a twofold axis, is just operating at a point. It's just a single thing. Now, we've already created these because we know they're compatible with all the rotations and mirror planes, right? So those are other two operators besides translation vector. But just because they're compatible, we didn't put in all the complexities that we could put in there. So for example, when we said we got to let these elements interact at a point and see what else they produce, what higher symmetries they produce. So for example, if I want to put a mirror plane with a twofold axis, what we're going to find out is that it actually creates another mirror plane like this, and it's distinct. So because I have two different ones, this is the original one that went with a twofold axis. So I have a twofold axis. I've got the original one, but I have to write it again in international notation because the other one is unique. It was induced by the fact that this one is here, and it created a unique one the other way. And so that's why there's a group which we haven't derived yet, a point group called 2mm. And of course, later we're going to take this group, we're going to take twofold axis, we plug it back in, right? And of course, we've already, done that with the trivial solution and the twofold axis, and all we get is the primitive lattice back, and we're going to call that P1 and P2, and we'll show you that. But these are the plane groups. We haven't done any of this yet, so we have to develop the rest of the point groups first. And you can see that here the 2mm isn't going to be compatible. Those mirror planes aren't compatible with the oblique, and you can see that, remember, because if it's oblique, there's no right angles and stuff like that in there, which you get from the mirror planes, for example, which is like rectangular. You can picture, okay, yeah, it's going to be compatible with mirror planes. So mirror plane we showed is compatible with those. In fact, we induced a centered rectangular from applying mirror plane in that lattice. We're going to be able to put 2mm's into these, and they generate a whole another spectrum of crystal structures, okay? Because now this thing I just drew here is repeated at every lattice point and induces other kinds of symmetry, right? So there's another one in the square as well, an additional one called 4mm, and then there's a 3m. We'll explain later why there's only 1m, and then there's 6mm. So basically, besides having our original 1, 2, m, 4, 3 that we already played with, we have to develop these other point groups which we haven't done yet: 2mm, 4mm, 3m, and 6mm. Now once we have all those, we go back to our lattices and we plug these in, developing, of course, this huge array, well, 17 of plane groups that can exist with all of the rules that we put in. So you can see we're doing here translation and rotation rules first, looking at point groups in it besides the rotations, also a mirror plane, and then finally letting rotations and mirror planes interact to produce more complex point groups, and then with all of these point groups, plugging them in and creating plane groups, which when we put atoms in will be two-dimensional crystal structures. And you can see here there's some notation that we're going to have to talk about. So that's the game plan for ahead. We're going to work on developing these additional point groups, and then we'll plug in and create plane groups, and then we'll be done with basically 1/3 of the course when we're finished with that.